And so it is about noise as with two elements, nuisance and constitutive. And I have to warn you, in a sense, I'm not a physicist, but I'm a mathematician, and therefore I don't like formula. Some people believe that formula would be the hallmark of mathematics, but that is, of course, not the case. But it's concepts. Anyway, let's see. How do we? So I will start with an example of drifting bottles in the Baltic Sea, then speak about one element, namely the constitutive element of noise or unprovoked variability, then noise as concealing element, and then pips and pops, something I've referred to already in the previous talk. And I mean, all this is also in the context of the nice title Angelica has chosen for this, for her seminar, namely Climate Science, what was it, from Hamburg, also born in Hamburg. I think that's a very nice thing, and so I should also embed that a little bit in the overall Hamburg context. Now, this is a diagram of an experiment which we had no intention to do. Namely, we had an event with school children. That was in 2019. We did that before as well. And we invited the school children to write letters which would be put in bottles and set out into the sea. So on the top left, you see one of these bottles. And and all these bottles were set out, were launched on the 15th of July, right at the point of the star. They were one after another, but at the same time, so within a minute or so, at the same location. Of course, the ship moved forward. And then the interesting thing is that we got a map where bottles were found. And so we found two in the west, I mean, Trelleborg and in Rügen. On the other hand, we had four or even more in the northeast, in Gotland and Öland. So how can that be? That these bottles move in so very different ways. They are moved by currents and by winds. And if we look at the time mean circulation of the Baltic Sea, as depicted in this diagram, then, well, essentially the bottles should have been moved out of the Baltic Sea, but they haven't. And if we look a bit closer, here we have a satellite image from 2005 of a block. So we have Sarajevo here, and Gotland here. So it's something like this here. And so we see that the Baltic Sea is full of eddies and other small scale features. And this seems to be important for our movement of the bottles. But we have to keep in mind, of course, the bottles are moved not only by the currents, but also by the wind. Now, so there is something like unprovoked variability. I mean, the details are unprovoked, not the fact that we have this internal variability. And here I have an old diagram from Eduardo when he did with a coupled atmosphere ocean channel circulation model. He ran it for 1,000 years. And the model is subject to periodic annual forcing of solar radiation, but otherwise no variable forcing is acting. So there's no CO2 increase, no volcanoes, no variable solar activity. It is a regular climate model. It simulates the full range of thermodynamical variables such as air temperature, sea surface temperature, currents, winds, blah, blah, blah. And what we find here is even if no forcing on timescales longer than 1 year, namely the 1 annual cycle, is present, the system generates significant persistent anomalies. On the top right side, you see for 1,000 years the European annual temperature. And so we have, for instance, here, for something like 50 years or so, an anomaly of 4.5 degrees. On the northern hemisphere, the anomalies are smaller, but nevertheless they persist for quite a while. And if we look at the spectra of these two things, then we see we have really lots of variance for low frequencies, small frequencies, even though the forcing is only there for 1 year. Here we have a frequency distribution. So we have variability here, which is not provoked by some external driver. Another one, a newer one, is here. So that's something what Beate Geyer did with others, and she was working with a limited area model of the atmosphere covering Northern Europe, or Central and Northern Europe, and she had two ensembles of extended simulations with the same regional model. And one ensemble of 5 members was initiated at different times, but exposed to the same forcing. So even though I do not remember the details, so one simulation was initiated on the 1st of August and another on the 1st of April. And then we started evaluating it beginning next January. When we have also another ensemble of 5 members, which ran with an identical setup, but on different computers. And so the interesting thing is the simulations show episodes of intermittent divergence in phase space. That's the term I invented for this. At the same time in all members of both ensembles, and that is demonstrated by the diagram on the right-hand side. On top, you see, I think it's temperature in Oslo. You see the temperature in Oslo in the 5 simulation, in the 5 trajectories. And you see there's a quiet phase in the middle, and it's quiet for all members. And then we have beginning in fall until, this is then another year. But this repeats in the different years. We have quite strong variations at the same time, namely in fall. And if we compare that with what happens in the platform ensemble, the same happens. And if we summarize the 2 top diagrams by the standard deviation across the 5 members of the 2 ensembles and calculate standard deviations for each day, we arrive at the bottom right diagram, which shows the standard deviations. And these 2 curves are virtually identical. So these episodes, when this happens, coincide with boundary conditions which impose a weak through flow. That means they provide dynamical conditions allowing for the minuscule noise to manifest in large scales. And the divergence may be seen as a proxy for the instationary local maximum Lyapunov exponent of the system. I mean, the tendency to show divergence of trajectories is, in a sense, the Lyapunov exponent. So this is interesting insofar as it seems not to matter how some very small changes are introduced sometimes in the system responds in the same way. Another experiment we have here is that was done by my student Tang Shenjuan, who's back in China now. He ran ocean models, namely a 3-layer nested simulation, one almost global, then with 1 degree grid resolution, then a West Pacific model, that's a larger red box with 0.2 degrees, and the South China Sea model for 0.04 degrees. The first model hardly describes macroturbulent eddy dynamics in the ocean, but the other 2 models become better and better in doing so. And here, the prescribed atmospheric forcing contains no weather. Only long-term monthly means are used. And also these forcing is strictly annually periodic. And so here we have for the South China Sea, that means we have here Vietnam, the southern Chinese coast for the different resolutions here. And this is the logarithm of the mean intra-seasonal variance, so the short-term variations of sea surface height in the South China Sea simulated in summer. And so here we have the coarsest, but there is, even though we have only the forcing with monthly means, we have intra-seasonal variability, which becomes stronger and stronger when we have higher resolution. Just as an introduction, this was meant only essentially as an introduction that we have this internal variability. Now, if we go then to the question, noise is a constitutive element. So the general statement could be noise causes low frequency variations and smoothing of tipping points in the climate system. And I will start to first speak about autoregressive processes of first order, then an example from energy balance models and the, I would say, famous numerical experiment by Mikolajewicz and Meyer-Reimer from '91. So autoregressive process, of course, wonderfully described in this wonderful textbook, which is only, almost 25 years old. And so what is an autoregressive process, say, of order P? If it may be written as in the formula 10.6, namely, it is a weighted average of the states, of the P states preceding time T, plus a white noise Gaussian forcing. AR1 is called white noise, AR0 is called white noise, AR1 is called red noise. And XT is independent of ZT. But of course, yeah, but it depends on what happened before. And so we have, and by the way, physicists like to call an AR1 process an Ornstein-Uhlenbeck process, which sounds, of course, much better. And here we have two time series for different alphas, that is this memory term, alpha y. If we have an AR1 process, then it's only one alpha, if we forget about the alpha 0. And then on top, you see alpha is 0.3, so that after one time step, 30% of the previous state is kept. And in the bottom, 90% is kept. And you see an obvious difference, namely that the episodes, the lengths of the episodes of the same sign are in the lower diagram much longer than in the upper diagram. Indeed, one calculates the distribution of the lengths of windows with the same sign. This is something like a spectrum as well. And so, in a sense, of course, if we look at this AR1 process, it may be understood as a discretized first-order differential equations. They have only one degree of freedom. There's nothing like which could oscillate as long as the damping coefficient is positive. And non-zero value xt at time t tends to be damped with an average damping rate of alpha per time step, but alpha has to be less than 1, of course. Now, how do the spectra and autocorrelation functions look? On the left, you see the autocorrelation functions, and with alpha equals 0.9, then this is when it slowly decays, and alpha equals 0.3 when it quickly decays. So this demonstrates how long an initial disturbance, which may be formed for whatever reasons, will reside in the system. And it's they're long with alpha equal 0.9. The memory is long, while the memory is short for 0.3. And the interesting point is the spectra shown on the right-hand side. So the top curve refers to 0.9, so the one with the long memory, and the other one to the, sorry, I did not mean long memory in a technical sense. I meant memory, the high alpha, and then with the low alpha. And the interesting thing is, so we have a system which is forced with white noise, that is with a spectrum which is flat. And what comes out is a spectrum which is red. And the larger the alpha, the higher the variance for long time scales. Now let's see what the noise does. We look at an energy balance model, so that the energy beta, yeah, this is wrong. E is equal to beta E, that's wrong. I must have something. It should be another character there. Well, beta E is the amount of energy which comes in, and alpha A is the amount of energy going out. And the equilibrium at the surface, say, of the ocean is then given as can be easily calculated. And if we have no atmosphere, alpha equal to 1, beta equals 0, then the temperature would be -4 degrees C, and with the present atmosphere, it would be 15 degrees. Okay, so that is well known. Nobody cares about it. The interesting thing is now when we integrate that in time, then in this case we use a temperature-dependent albedo. Shown on the right-hand side. The idea is if we have it, if it's warmer, then there would be less, the cryospheric area would be smaller than in case that the temperatures are lower. And therefore, if the temperatures are higher, then the temperature albedo would be lower compared to the other case. And the effect of this is that conditional upon which value we start, we end up with two different states. One referring to is warmer and the other is cooler. And so we have a nice, if we go across this, the critical value, then we have, a, so to speak, a tipping point. But if we now randomize the transmissivity, which could account for the fact that clouds vary to some extent randomly, and we're not doing it strongly, then the time development looks very different. Namely, we have now seemingly that there are still the two long-term solutions or states, but the system flips between the two. And we get a temperature distribution which is bimodal. So this is a very different character. And so here I have two more, a paper by Timmermann and Lohmann, who spoke about noise-induced transitions in the simplified model of the thermohaline circulation. And also I found a book, unfortunately I have not gotten it now, but at least in the 1980s, this seems to have been a hot topic. And now the Mikolajewicz and Meyer-Reimer experiment. So what they have done is they use an ocean model, which was forced with standard stationary forcing concerning wind, heat, and freshwater fluxes, and they added random zero mean precipitation field. And the forcing is thus, the time-dependent forcing is white noise, and that is shown in the lower diagram as a almost horizontal line. And what the system does, and this is the mass transport through Drake passage, that is given by this curve here. This is obviously red, or kind of red. I mean, it has actually a peak here. If that is realistic or not, that's another story. But what we see here is the time development. And so in the beginning, first say 100 years or so, the system doesn't do anything, mumble, mumble, mumble. So we think, what do we do? And then it starts to do something in an irregular manner. So it shows the typical stochastic behavior, which is summarized by this here. So this is transforming something totally unorganized into something organized. If this mode, which is excited by the noise, is realistic or not, that's another story, but at least it's an interesting experiment. And I would say it's one of the classical ones. And by the way, this is also a demonstration of the Hasselmann's stochastic climate model at work. Now, the other element of noise is the concealing element. And the presence of noise hampers the identification of force changes in models, but also in the climate system. And so first we'll touch interpretation of numerical experiments with dynamical models. And here I have a case from Ralph Weisse, the influence of the shape of the ocean surface waves on atmospheric state. And the second case is identifying the effect of anthropogenic influences on regional climate, the detection and attribution complex. And here the example is recently changing climate statistics and their relation to elevated greenhouse gases and changed land use. Now, this is noise as a nuisance and masking the signal. And I've shown the other day the same diagram here. That is from the 1970s. So that is before the Max Planck Institute was set up. And that was what people had in mind is, and so we have a small number of deterministic cycles, 1 year and 1 day, for instance, but otherwise we have a full spectrum, so we have variance at all timescales. It's not the sum of spikes, but it's something continuous. And variations are ubiquitous in the climate components, in particular the atmosphere and oceanic dynamics. Some variations may be externally forced, in particular the annual cycle, but many are not. They are unprovoked by external factors and represent a kind of smoke without fire. The latter is called often noise. But not in all quarters, and I had quite disturbing reactions by reviewers when they said noise has something to do with whales and them getting sick and whatever, or inaccuracy of numerical schemes. Now, we have seen noise may be constitutive for atmospheric and ocean dynamics, but it hinders the identification of causes and influences. And we have seen that the mathematical concept of stochastic processes has turned out to be powerfully describe such noisy variations. It really doesn't matter if there's really randomness, but it is so complex that we cannot disentangle it, and so that this mathematical concept is useful in describing what is going on. And so let's briefly go back to this issue of how do we detect or find that there's something, and then we usually use statistical tests of null hypotheses, and so we just want to discriminate something called signal, a provoked change, so to speak, to noise, the unprovoked part. That was introduced, to my knowledge, 1974 by Chervin, Gates, and Schneider. And interestingly, Larry Gates lives now in Hamburg. And it took a long time until other communities understood that this is not only an issue of global atmospheric dynamics, but also of ocean dynamics and on regional scales. So the null hypothesis is that the observed change is related only to internal variability. The alternative is then that at least part of the observed change is caused by external factors. And as usual with statistical tests to discriminate, we build a random variable S, which describes the outcome of the sampling process if the null hypothesis is valid. When we have a distribution of S, and if our delta, the observed change, is larger than the pth quantile of S, that is, given the null hypothesis, with a subjectively chosen P, then the occurrence of delta in a regime given by the null hypothesis is sufficiently rare. Of course, P must be a large value, a very large value, so that we conclude that the null hypothesis is false and the alternative hypothesis is accepted as valid. Keep in mind, statistical tests are asymmetric. The outcome is either the rejection of the null or the non-rejection of the null. The former is taken as evidence for accepting the alternative as true. The latter represents insufficient evidence for the alternative, which is not to be taken as alternative as false. Now, this is then the experiment of Hans. He worked with an atmosphere-ocean wave model, long forgotten, Eckerbaum, and he ran 2 ensembles of simulations. The control one where the sea surface roughness, was obtained using the standard Charnock relationship for the exchange of momentum from the atmosphere, to the waves. And the other one, ESD, I forgot why it was called ESD. Then the impact of the waves is explicitly accounted for in the sea surface roughness using a wind over waves coupling theory. So in one case, it doesn't matter how old the waves are, in the other case, it does. And this is the region which was considered. So we have here Greenland, Ireland, Iceland. And here's the results. So in the lower diagram, you see again the map. And this is the difference, the solid or dashed lines are the difference between the 2 ensemble means, and we have relatively large values south of Greenland. But the interesting thing is, if we do a statistical test, just a local t-test, where would we reject the null hypothesis? This is the dashed areas, the stippled areas. So the largest changes do not coincide with the strongest signal, but it may be that the internal variability is simply largest there, while in parts further south we have small differences, but they are statistically significant, which does not mean that they're physically significant. So I think this is a very nice example of demonstrating the role, the need to do statistical testing. But it seems that the regional oceanographic community, until maybe recently, did not do anything of that sort, but just compared, looked at the results here given in terms of the lines, irrespective if there's it can be discriminated for noise or not. Now, the other one is the detection attribution. And detection means we determine if observed variations are within the limits of variability of a given climate regime. If this regime is undisturbed, this is internal variability, of which and so forth are part of. If not, then there must be an external mix of causes foreign to the considered regime. This is done as a real test, while the attribution is something else, namely if we have found that there must be a cause foreign to the considered regime, then we say, okay, we have to find, we should search after plausible mechanisms, and we determine a mix of plausible external mechanisms that best explains whatever the word explain means, the detected variations. And this is what Klaus Hasselmann did in, it was part of the package of the Nobel Prize for Klaus Hasselmann. The 1979 paper is awful. I mean, it's really hard to read. It was for him, Klaus, very clear, but for others not. But in 1993, he repeated, he wrote it up again, and then suddenly it was wonderfully clear. So, yeah. And I will speak more about that in the next week's lecture. But I have two examples here. And again, it's on the Baltic Sea, and I'm happy to see Markus Meyer here. So this was a study which did with Armine Bakondarian, who's back in Hamburg, by the way, now. And she considered the issue of regional detection. The global detection has long been done, but the question is, can we also detect change in the region, and can we attribute it to what causes? And here we examine the 1982 to 2011 temperature trends in the Baltic Sea region. Here we have the gray bars here for different seasons, shows the temperature change in Kelvin per decade, winter, spring, and so forth. And we have, we estimate the variability, the internal variability from 2000-year Palomar simulations. And then we see that the value of in December, January, February could also be consistent with no change. It could be related, could be entirely noise. Chances are slim, but could be. In spring, this is no longer the case, and also in July, in summer and fall. So in these three cases, and also in the annual condition, we would say, no, there is something which needs to be explained. So the recently observed annual and seasonal warming of the Baltic Sea area is significantly different is inconsistent with the explanation that it's just internal variability, except for winter, where there's a small chance. Now, this was the detection part. If we go to the attribution part, then we thought, well, maybe it's the greenhouse gas signal, which is we see here. And so let's, we have now green bars here as well. The green bars have these black whiskers. And the black whiskers indicate, no, the green bar is the suggestion of the response if an A1B emission scenario would be in place for this time. So that's the average across 10 simulations from the ensembles project. And the width of the ensemble suggestion is given by the black whiskers. And so even though in December, January, February, we cannot exclude that it could be internal variability, we see that the models, if it would be greenhouse gases, the models are pretty good in describing what is going on. And this is also so in May, April, March, April, May. So we can say, yeah, okay. In winter and spring, we can say we see a signal which is consistent with the greenhouse warming according to A1B. Actually, the emissions of A1B were similar during that time. But in June, July, August, and in fall, something else happens, namely in June, July, August in particular, the warming is much higher than what the model suggests, even if we take the uncertainty into account. And this is also so, even less strongly, in September, October, November. So we can explain the changes in winter and spring dominantly by greenhouse gas-driven scenarios, but none of the 10 RCM climate projections capture the observed annual and seasonal warming in summer and autumn. So there must be something else. And it is a plausible hypothesis what that may be is the reduction of the aerosol load at the same time. But this is a hypothesis, and we have not been able to really verify that greenhouse gases plus aerosol change would allow to decompose the warming, the strong warming in the Baltic Sea region in the summer. Now let's come to the last part, the PIPs and POPs general concept, and I've spoken about that last time already when I spoke about Klaus Hasselmann, and I suggest that is the main paradigm shift he introduced. Unfortunately, we have no good examples of low-dimensional nonlinear dynamics, such as the low Lorentz system encapsulated in the PIPs, but many examples for the linear variant, the POPs, and I will show an example. An almost trivial example is the stochastic climate model, but also the concept of detection and attribution may be understood in this framework. And the concept is also part of all crazy realistic dynamical models which carry parameterizations in them, because then we also have a separation between a signal space and a noise space, and the effect of the noise space on the signal space is taken care of conditional stochastic models called parameterizations. So those of you who have seen that before, I'll ask for your understanding. So if we think the whole process is given in this way, so we have numerous external influences and lots of processes, small and large, and how we measure small and large, I don't know. And so we look at this system and we want to make sense out of it. And so the idea with the PIPs is to say, okay, for the problem at hand, this depends on the problem, we select those processes which we consider as dominant for the dynamics, and this is given by the blue dashed line. And then, of course, the problem dependent, so it would apply only for certain spatial and temporal scales and a range of parameters. And so from the full system is reduced to this reduced system, and the trick is that the influence of those processes which are not included is described by stochastic as conditional stochastic models, saying if the resolved scales, here P1, P2, P3, and so forth, are in a given state, then at the same time the unresolved scales will, on average, or will have an influence on P1, P2, P3. And this is given by a certain stochastic, can be described stochastically. And so in most cases, we just use the conditional expectation. That is the character of a parametrization. So the PIP system, that is the smaller system, takes into account all processes which are really significant or which are considered really significant for the considered dynamics and parameterizes the effect of all other processes. And we can find out how good this model is, but to test, namely to see how good the reduced system is to predict the considered dynamics in the full space. And so this is closely related to normal modes. And so we briefly introduced that. So let's assume that we have an equation of the type 1. And of course, you will see this is very closely related to an AR1 process, namely that the state at time t is a linear function of the state x. X is a vector this time, plus some forcing. And so the B, this is a matrix, and this will have eigenmodes, eigenvalues. And so we will have quite a few eigenvalues and eigenvectors. Some of the eigenvalues will be complex, but then they appear in conjugate complex pairs. And we can expand the original field X into, according to Formula 3, into a series, into a short series spanned by the first or by all eigenvectors. And then we have for each of the normal mode coordinates, the AKs, one equation, namely one-dimensional or complex dimensional, which is a standard diagonalized damped harmonic oscillator. And then we can also give the solution. So the alpha k, if it's complex, describes a rotation in space, a damped oscillation in space, and we have two characteristic numbers, namely the damping time and the period. Now, the trick with the POPs is then that we say, okay, we are not going to the dynamical equations, but we try to derive them from observations. And so that is easily done. So this B is given as a product of C1, that is the leg 1 covariance matrix of X, times the inverse of the leg 0 covariance matrix. And to actually do so, then of course the dimension of X must not be too large, because otherwise we have a covariance matrix which we cannot deal with. And so we usually first project the very large scale X onto just a few ones. This is reminds on the signal space. Very often we just use empirical orthogonal functions. We can also sometimes we do some time filtering if we want to focus on something special. And so the interesting thing is when we have a complex eigenvector with real part P1 and P2, then these eigen solutions tend to build sequences of the type given here. Namely, if we see the pattern P1 minus P1, then after a quarter of period, we tend to see P2, and after another quarter of a period, we see P1, then after a quarter of period, minus P2, and so forth. And these are the POPs. And we've done that several POP analyses to determine the Madden-Julian oscillation in the tropical troposphere. This is a phenomenon which travels, tends to travel as a wave number 1 pattern eastward across the globe within 30 to 60 days. We heard a seminar by Roald Madden earlier in this series here. And what we did is we analyzed daily fields of a controlling velocity potential at 200 hectopascal. We have subtracted the annual cycle and filtered with the first 10 EOFs. And we have retained the variability only on 30 to 90 days. And we got essentially one useful POP, and that is shown here. So it's just on the equator, and I've described so the P2 and P1 and described the oscillatory behavior. So if we see P2, then after a quarter of a period, which is something of the order here of 15 days or so, we tend to see P1. And after another period after another 15 days or so, we tend to see minus P2. That is, the maximum sits then over about South America, 120, or the nonsense, the Eastern Tropical Pacific at 120 east or so, and after another 15 days, we will have minus P1, so the maximum sits at 120 west or so. So it's this moving around the globe, but it's a damped thing. So if it really fulfills a full cycle, it's a different story. And we have here for 1985 the pop coefficients, which behave nicely irregularly, but also you can see the phase difference of the two very nicely, saying how the different patterns change. How does it look not only along the equator, that is shown in the two lower diagrams, and I'm not sure if you can see where's what. Oh, oops, I wanted to persuade my mouse here. So where's what? Here we have Guinea, we have South America here, and we have the Horn of Africa here, and the equator is here, of course. And then you see that it's really something concentrating along the equator and moving in an eastward direction with different speeds. So when it is sitting in this part here, it's moving slowly. If it goes from here to there, it's really getting faster. We also use that to do forecast experiments, and that is shown in this diagram. And here we have a case that we have a strong initial state, so strong large values here. And then we start, I'm not sure where we start. Not sure where we start, somewhere here. And the pops would tell us it's just essentially, if we forget about the damping in this way, and what we actually saw is this here. So it is really moving in this way. Of course, it's not overly accurate. And if we go for the autocorrelation skills of forecasts, conditional upon the intensity at the initial time, so we have here very, very strong ones, the dotted ones, and all cases, then we see that we really have quite some persistence in the motion, in the circular motion, up to 24 days, while if we look at a simple persistent forecast and a one-dimensional persistence, the skill is gone after, say, 7 days or so. Yeah, but if we have not a strong MJO in the beginning, then the skill is much lower. So let me conclude this now. So noise is here understood as internally generated variability, which cannot be traced to external drivers, so with smoke without fire. It is conceptualized as stochastic variability, possibly conditioned by some state variables. Noise is ubiquitous in the climate system on all scales. Due to myriads of nonlinear mechanisms, and it doesn't matter if this variability is real stochasticity or if it is just impossible to discriminate the variability from stochasticity. It does not matter if God is rolling a dice, as long as we cannot discriminate his doing from doing so, we can consider that. And real stochasticity is the most useful mathematical construct. The presence of the noise changes the dynamics of the system. The mean circulation would be different if there were no storms. The storms were different if there were no convective cells and so on. And a major thing is the noise hinders the identification of externally forced signal and the utility of forecasts and the attribution of anomalies to specific causes. Before Klaus Hasselmann introduced the stochastic climate model concept, and more so in recent times, people are convinced that all remarkable developments in climate must be related to one or more external reasons. But Hasselmann demonstrated there smoke without fire, climate variability. Low frequency variability is generated as the integrated response to short-term fluctuations. For instance, macro turbulent atmospheric flow at mid latitudes. Thus, we have a new task for climate analysis, namely the identification of a small space within which the dynamics of the considered signal rules, while the remainder acts in the spirit of the stochastic climate model as stochastic forcing. This is the Pips and Pops concept. Thus, if we have C changes, these are a result of both external and internal stochastic forcing, external forcing and internal stochastic forcing. And the question arises if an anomaly is just internally generated low-frequency variability or caused in part by specific external causes, that is the detection attribution. Now let's have on the final diagram, thing back to the Baltic Sea. We have here a simulation of the displacement of particles thrown into the Baltic Sea at red point. And we have here two simulations which differ, in which we have random displacements at each time step. And we see that in this way we can generate very different trajectories. One which leads within 90 days or so to the Lithuanian coast, and the other one which where the bottles remain in the western the Baltic Sea, almost reaching our summer cottage at the far left side. Marcus Meyer's summer cottage, I think, is not affected. It is outside of this map. This ends my presentation. Thank you very much.